In the last video, I talked about arrays and creating arrays in Octave. Once you've created your arrays, though, you still need to be able to use them effectively. One important thing that you need to be able to do is to extract specific elements from the arrays. Elements in an array are specified by the row and column numbers in that order of the element. In Octave, the row and column numbers are placed in parentheses after the array name. The row and column numbers must be separated by a comma. Numbering of rows and columns always starts with 1. Elements of one-dimensional arrays can be addressed by a single number, either the row or the column number. These conventions are true regardless of whether you're creating an element in an array or you're accessing an element of an existing array. Suppose that this array already exists in the workspace. I can extract the element in B that's in the third row and the second column, this value here, by placing 3, 2 in parentheses after the variable name. This syntax is equivalent to the number 6, which I've then assigned to a variable named C. The point is that the number at this location in the array can be used just like any other variable. Colon notation can be used to access ranges of elements in an array. The approach is similar to that taken when creating arrays, but the desired elements appear within parentheses after the variable name, and all of the values have to be integers. We still specify a beginning value, an increment, and a final value. The first index is specified by start_ind. Subsequent indices are created by adding the increment to the previous index. The command stops creating indices when the next value in the sequence exceeds the value specified by end_ind. A colon by itself returns all of the elements in that dimension of the array. If you don't specify an increment, Octave counts by ones. Let's do a couple of examples to see how this works. Say we have this array B present in the workspace. For future reference, I'm going to number the rows and the columns. This is the first, second, and third rows, and the first, second, and third columns. Now, if I execute this command, the array C will be equal to the elements of B, and the rows will start out at 1, they'll increment by 2, and end at 3. So the first array index in the row position that we'll get is 1, 1 and 2 is 3, and we're done. So this gets elements of B in the first and the third rows. The syntax for the columns is the same, so that will also pick up the first and the third columns. That means that I'll get this element, this element, this element, and this element, and the array C becomes 1, 0, 5, 9. Now let's look at this example. My row numbers start out at 1. There's no increment specified, so I increment by 1s and end at 2. So the first element's 1, the second element is 1 plus 1, which is 2, and then I'm done. The columns just have a colon. That means I want all of the columns in those two rows. So it's this row, and all of the columns, and D becomes 1, 2, 0, 3, 7, 0. As an example, I'll create a vector named Z, which starts at 0, has increments of 0.1, and ends at 1. Now I'll use colon notation to access specific elements of the array. I'll extract the elements of the Z vector that have even indices. So I'll type Z_even, which will be my new variable, equals Z of 2 to start at the second index, incrementing by 2, and going to the end. End is an easy way to get the address of the last element of an array in any dimension. Our new array contains the second, fourth, sixth, and so on elements of the original Z array. When you're working with arrays, you always need to be aware of the difference between the indices, which tell you where the numbers in the array are located, and the values themselves, which are the actual numbers in the array. One reason for this is that the indices in the array have to be real positive integers. Remember that the first row and column in an array are always numbered as 1. Subsequent rows and columns will increment by 1. The second column is column 2, the third is 3, and so on. This might seem like a case of stating the obvious, but this convention isn't universal. In the C programming language, the first index is numbered as 0, and in Fortran you can define negative indices. Anyway, there generally aren't those types of restrictions for the values in the arrays. You can usually assign any number to an array location. There are some exceptions to this if you define a logical variable or a string, but we won't worry about those just yet. For example, the designation A with 0.3 in parentheses after it tries to get the 0.3 element in the array. No such element exists, and you'll get an error message. It is, of course, perfectly legitimate to assign the value 0.3 to an array location. For example, the fourth element of the array A can be 0.3. As another example of accessing elements of arrays, I'll talk about using arrays to define indices for other arrays. Suppose we have these two variables defined in our workspace. If I execute this command, the array B is put in as the indices of array A. These values are used as indices. So the first time through, I look for A of 3, which is negative 12. That's going to be the first element in the A array. The next one will be A of 5, 1, 2, 3, 4, 5, which will be 8. And the last one, a 2 will go in here. I'll pull out A of 2, which will be 7. Now let's look at another command. If I say C is equal to 1, 0, negative 3, and then try to access A of C, I'm okay with the first element. 1, A of 1 is 0. However, A of 0 isn't defined. MATLAB doesn't know what to put in there. A of negative 3 isn't defined. This command will simply result in an error message. This data provides the sound speed in water as a function of temperature. There are really two types of numbers here. The first set of numbers is a group of temperatures, and the second set is a group of sound speeds. It makes sense to assign these two types of numbers to different arrays. So I created an array named temp, which contains all the temperature values, and another array, SSPD, which contains the sound speed data. Notice that I maintain the same order of numbers in each of these arrays so that the first element of the temp array corresponds to the sound speed provided in the first element of the SSPD array. The second elements correspond to a pair of data, likewise with the third, the fourth, and the fifth elements. This is important because if I want to relate the numbers in these two arrays, I have to do that by their positions in the arrays. These two arrays really don't know anything about each other. I have to keep track of what corresponds to what. Now, suppose I want to display the sound speed, which corresponds to the temperature at 180 degrees Fahrenheit. First, I need to find the index of the 180 degree temperature in the temp array. That's the fourth element in the temp array. So to find the sound speed at that temperature, I go to the fourth element in the SSPD array. So I type SSPD of 4, and the number 5095 will be displayed. Next, what I'd like to do is find the temperature which gives the maximum sound speed and what sound speed that is. The maximum sound speed can be found just by looking at all the sound speed numbers and picking the largest. It's 5101, which is the third element in the SSPD array. The temperature corresponding to this sound speed is the third element in the temp array.
So if I want to save these values as separate variables, I can assign SSPD_max as SSPD of 3. So this will get assigned 5101. And temp_max is temp of 3, which will save the 160-degree temperature. In this example, I've measured a voltage in an electrical circuit as a function of time. I did the measurement using an oscilloscope, which allowed me to save the voltages and the corresponding times at which they occurred. The oscilloscope I was using allowed me to store the time and voltage values as ASCII data, and I saved the resulting files in Octave's current working folder. I want to find the maximum voltage and the time at which this voltage occurred. The file containing the time data is named time.txt. I can import this data with the load command. Just type load space, the file name, time.txt, a space, dash ASCII to let the load command know that it's expecting ASCII data. The file containing the corresponding voltages is called volt.txt. Load this file by typing load space volt.txt space dash ASCII. Now I've got two variables, time and volt, in the workspace. Sadly, it'll be hard to find the maximum voltage value and it's indexed just by scanning down the values. For example, if I display the voltage values by typing volt and pressing enter, I get this mess. Octave has a function named max that finds the maximum value in an array. I'm guessing that I can use this function to find the maximum voltage, but I also need to find the index where the maximum voltage is found. This index will let me find the time at which the maximum voltage occurred. Let's check the help files to see how to do this. Type doc max. It looks like max will return both the largest element in the array and its index with this syntax. So to get the maximum voltage and its index, I can type max volt, comma, max end. Those will contain the voltages and the indexes, equals max of volt. The maximum voltage is about 1.53 volts, and it occurs at the index location 65. To find the corresponding time, just type time of 65. The time is 0.32 seconds.
Now that we understand how to create arrays and access specific array elements, we can talk about some special purpose arithmetic array operators that are available in Octave.